Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in Electronics and Communication Engineering, Dundigal, Hyderabad. Today we are going to discuss the questions related to Module 2, which is Interfacing Devices under the course Microprocessors and Microcontrollers. First question is, demonstrate the assembly level language program to generate the RAM wave using DAC. So for this, we have 8086 processor. This will send the digital data for DAC. So where we are going to connect the IO device to the 8086 processor through 8255. So this DAC will generate the analog signal. Here we are interested for generating the ramp signal, where the ramp is going to have the patterns are generating starting from 00 to high band. So here 8086 processor will send the digital equivalent starting from 00 to maximum value FF. Once it reaches to FF, again it will start from 00 to FF. So if you write a continuous loop, it is going to generate a series of a ramp signal. So first we will write assume CS colon code for assigning the segment for code. Start up the code segment with code segment. First we have to initialize the control word register of 8255. Here only the port A we are using, and the remaining ports we are not using. So the control word register for 8255 is, this is for port C lower, port B, group B, mode, next port C upper, port A, this is group A mode. As it is IO mode, the MSB bit is 1. In this example, we are converting the digital to analog signal, where the digital value from the microprocessor will be given to DAC through port A. So that is also port A will be connected in output port. So port A is equivalent to 0. The remaining ports we are not using, so these are don't care. As we are not using any port corresponding to group B, so the mode also I don't care. And port A, which is belongs to group A, and we are using in a simple IO mode, that is mode 0. So you will write the mode bit as 00. So now the pattern which we are going to get for the control word register is 1, 0, 0, 0, and the remaining 4 bits are don't cares. So where for this don't cares, we can pass the values from 0, 0, 0, 0 to 1, 1, 1. Any value we can pass, but we are taking the default values as 0. So we will write the control word register value as 1, 0, 0, 0, 0, 0, 0, 0, which is equivalent to 80H. So for writing the control word register, first the value which we want to write for the control word register will be moved into AL register, that is move AL, 80H. Then we will write the out instruction we want to send for the control word register. So out control word register address, AL. So as we are not given with the address of the control word register, a generalized notation I am using. So if the address is given, the corresponding address we can place in the control word register or port. Next, as we know, for a generation of a ramp signal, we want to pass the initial value is 00 till FF. So move AL, 00, 0. So first value we want to send to port A, so that you will write with out port A, AL. So when we execute this instruction for first time, so 00 will be passed for conversion. Then for generating the next number, that is 01, so we go for incrementing AL. We want to generate until FF. So we will compare AL, FF. If the AL contents are not equivalent to FF, again redirect to L1. So jump on carry, or we can write jump on carry or jump on non-zero. Because here AL is less than FF, so which will make the carry flag is equivalent to 1. So when carry flag is equivalent to 1, so we go for generating the next pattern to the port. Next, for getting a continuous iteration, just we'll jump for loop 1 unconditionally. Then to terminate the program, however it is infinite loop, it is going to generate, but for terminating the program, we will generate int21h with a function call of 4ch in AH. We will end the code segment using code endes. We will end the program by using end start directory. The next one is demonstrate an assembly language program to convert unlock to digital using 8086. Here also we have the 8086 processor, and it has to control the ADC, where for this ADC we may have 8 different IOs are existing that we can generate through the select lines. So once the corresponding IO is generated, the particular input which is selected by the select lines will be given for conversion through ADC. Once it is converted into digital, the equivalent value will be read by 8255. From 8255, the converted value will be read by the 8086 processor. So for conversion of this unlock to digital conversion, we have to generate first SOC pulse. Once the SOC pulse is given, wait for end of conversion. If EOC is equivalent to 1, it indicates conversion is done. Suppose if EOC signal is not generated as 1, it indicates still the conversion is taking place. So when the conversion is taking place, again we go for a repetition until EOC is equivalent to 1. So once the EOC is equivalent to 1, so we go for a step 3, otherwise you will go to step 2. So in the step 3, just we will read the digital equivalent, which is generated from the ADC. So for converting the unlocked signal to a digital conversion, here various signals which we require are the select lines we have to generate. So that usually will connect through one port. I am taking port B. Next, the EOC signals and SOC signal, two control signals are needed. One is input and the one is output. This will connect through port C. So once the conversion is done, the third step is we want to read the digital data or digital equivalent, so which will be collected on port. So for writing a program, first we have to write the control word register. So where we are using all the three ports, port A, port B and port C. So this is the schematic representation of interfacing of 8086 for unlock to digital conversion, which is 0 to 08, where you can see the 8 pins inputs are connected, where we can apply 8 different unlock signal. Which unlock signal we want to convert, that will be selected by passing the select lines through some address lines on ADC. So once the input is selected, then we will give the SOC pulse. Once the SOC pulse is given, then we will check for use. So the SOC pulse, just will give a pulse as 0, 1, 0 as SOC. So once EOC is equivalent to 1, then we are going to read the equivalent digital 8-bit data. So the program for this one is assume CS colon code, then a code segment for start of the code segment. So first we have to write the control word register of 8255. So in this, the format is which is a 8-bit. The LSB is for port C lower. The next bit is port B. Next one is mode for group B, port C upper, port A. Next one is mode for group A, the MSB bit is equivalent to 1. Here the mode of operation for both group A, group B is mode 0. So first you will write this. And port A, that we are used for reading the data. So this we are going to connect in input mode for 8086 processor. So by configuring 1. Next, the port C lower, which is going to give for SOC signal, which is a output signal. So this will write as port 0. Port B, which is a select line. So 8086 processor will send the data to selection of the port. So you'll write port B is also equivalent to output port. Whereas the EOC signal is connected to port C7. So this is a input signal to the processor. So the mode of operation is 1. So now the value which we want to write for the control word register is 1001 1000. So the equivalent value is 98. So the value which we want to write for control word register is 90H. So first we will move the 98H into AL register. From AL register we will out that one to control word register by using out instruction. Next one is we have to select which input. So input is given on port B. Here we are selecting the input which is connected to I input 2 pin. So we will write the control the value for port B is equivalent to 02. So first we will move the 02 into AL. From AL to port B is here. So here we have selected the input signal. Next we want to give the SOC pulse. So the SOC pulse is connected to port C lower, that is PC0. However, the remaining bits are not used because we want writing the data to port C. So first you will write 00 to port C. Here the SOC pulse we are going to give in this fashion 0 1 0 for SOC signal. So the port C signal first you will write 0, then you will write port C is equivalent to 1, then you will write port C is equivalent to 0. So a two set of instructions you will write for 0 0 0 1 and 0. So then next instruction is move AL comma 01H. This we are going to write for port C. So out port C comma L. The next value we have to pass is 0. So you will write move AL comma 00H. Then we will send this AL contents to port C. So we will write out port C comma AL. Now EOC signal is generated. Once EOC is given, the conversion will be takes place. So we can know that the conversion will be done by reading the EOC signal. So the EOC signal is connected to port C7. So for this, checking the status of the EOC signal, we will read the port C. So for reading the port C, we will write the instruction move in AL comma port C. So this is for reading the port C. The purpose of this one is we want to check EOC signal. So EOC is only one bit where it is connected to port C7. So whatever the value which were read in accumulator, we want to check the port C7 bit, which is a EOC signal. So for checking this, we will shift these contents or rotate these contents towards left side by 1 bit. So either we can write SHL or SAL or ROL or RCL. Any instruction, just we want to check MSB position. So once accumulator contents are loaded with the port C, for checking EOC signal, we will rotate AL contents towards left side by 1 bit. We are using SHL AL comma 01. When we shift these contents towards left side, the PC7, which is nothing but EOC signal, will be given for carry flag. So if carry flag is equivalent to 1, conversion is done. So we can read the data. If carry flag is equivalent to 0, conversion is not done. So again go for reading port C. So we will check if carry is equivalent to 0, again go to loop 1 for reading the port C. For that you will write JNC loop 1. So this loop will be iterated until EOC is equivalent to 1. Once UOC is equivalent to 1, conversion is completed. So carry flag is equivalent to 1. The condition fail, it will come to next line. So in the next, once UOC signal is generated, we are going to read the digital equivalent which is on port A by using in AL comma port A. So whatever the data which we are read on port A, that will be collected into accumulator. Then we will end the program by generating INT21H with a function called 4CH into AH register. Then we will end the code segment by using code endes, and we will end the program using end start. This is program for analog to digital conversion interface. The next program is about demonstrate with assembly language program to interface stepper motor with 8086 processor and rotate in clockwise rotation. So for stepper motor, the rotation will be takes place stepwise. After every step, we will give some delay, then it will be go for next rotation. So here we have total 4 excitations, 4 windings, that is winding A, winding B, winding C, winding D. Initially, we can excite any one of the winding. Either we can start with the winding A or winding B or winding C or winding D. Suppose if we are exciting with the winding A and the remaining windings are given as zeros. For rotating in clockwise, windings will be like this: A, B, C, D. So this is one winding, this is one winding, this is one winding, this is one winding. For rotating in clockwise, we will excite first A, B, C and D. Again A, B, C, D, A, B, C, D like this. So next we are going to excite winding B. Next we will excite winding C. Next we will excite winding D. So the value which we can write for this one is 11H. This is 22H. 44H, 88H. This is for clockwise, one winding at a time. If you are going for 2 windings at a time, AB one time, BC second excitation pulse, next one is CD, last one is DA. Like this 2 winding excitation is also applicable. So now for interfacing this 8255 to the microprocessor for stepper motor interfacing, we require the stepper motor with the 4 windings, winding A to winding D. These pulses we have to send from 8086 processor. However, in between this processor and stepper motor, we have 8255. As we are sending only pulses, one port is sufficient. So we are going to use port A, that is also in output port. So when you are writing the program, first we need to find out the control word register of 8255. The control word register of 8255 is, this is port C lower, port B, mode for group B, port C upper, port A, and these are mode for group A. The MSB is 1. So as the mode of operation is 00, that is mode 0, we will write the mode of group A is 00, and we are using port A, that is also in output mode. So the port A bit is equivalent to 0. Remaining ports are not required, so they will become don't cares. So from 80H to 8F we can give any value. So by default values we will take as 0. So we will send 80 to the control word register. So for sending the control word register, we use the instruction move AL comma 80H. Then we will send move out control word register comma AL. So once the control word register is configured, then we have to give the pulses for the excitation. So for excitation, either we can give 11H or 22H or 44H or 88H if it is single excitation. So for sending this, next how many times we want to rotate. So for that we are going to be place some count in CX register. So how many pulses we want to send, how depends upon how many rotations we require. So next the pattern which we are going to send is 88H. So either it can be 11H or 22H or 44H or 88H. Any pattern we can send. This will be sent for port A. So once this pattern is generated, one of the winding is excited. Now we want to excite the next winding. So before that, for each and every rotation, we are going to provide some delay. So we'll call the subroutine with the name delay. So call delay. So once the delay is done, then we are going to rotate these contents towards a right side by 1 bit by using ROR AL comma 01H. So it depends upon how we are connected. So winding A, winding B, winding C, winding D. Here it is connected port A3, port A2, port A1, port A0. So first we have sent the 8. So next I want to excite winding B. So these bits we have to shift towards the right side. So for that purpose we will use ROR AL comma 01H. So as one excitation is done, then we are going to decrement the count, where the count is specified how many rotations we require in CX register. So decrement CH. So once the count is equivalent to 0 in CX, it indicates the number of rotations for stepper motor is done. If CX is not 0, still some more pulses we have to send. So for that purpose, we will check J and Z. If it is J and Z, we will loop. Otherwise, it will come out of that. So as the number of rotations are done, so we can terminate the program by calling interrupt 21H with a function call of 4CH in AH register. Then we will end the code segment by using code ends, and we will end the program by using end start. So this is a program for interfacing a stepper motor with 8086 processor. Next we will move to the next question. So demonstrate an assembly language program to generate a square wave. So for generation of a square wave, so square wave is nothing but a series of pulses. So we are going to send only two values, low value and high value. So we had to send this 0 for some amount of time. So this we are going to provide with a delay. Here also will give delay. If it is a symmetric, this delay value should be same. If it is asymmetric square signal, you can have two different delay programs. So we are considering symmetric signal. So we'll call a delay with the same value for 0 and high value. So the starting value, either it can be 0 or it can be high value, FF, anything we can pass. So for writing the program, in the interface, 8086 is connected to the DAC, which will generate the square waves. We have to send the digital pulses from the processor to a DAC, where we require only one port of 8255, that is port A, and it is configured in output port. So for generating the square wave, in the program, first you'll write the control word register for 8255. The control word register for 8255 is port C lower, port B. Next one is mode for group B, port C upper. Next one is port A. The next two bits are mode for group A and MSB is 1. Here we are using only port A, that is also in the output port. The remaining ports are don't care, and the mode of operation will take as 0. However, port B we are not using, that is also will be don't care. So here also I'll take this one as don't care. So what is the value we had write is 1, 0, 0, 0, and the remaining 4 bits are don't care, where you can pass the values from 0, 0 to 1, 1, 1, which is nothing but from 80 to 8F, any value we can pass, but we are taking the default values as 0. So we will send 80H to the control word register by using the instruction move AL comma 80H. Then we will output this one to control word register out CWR comma AL. The next step is we need to send the pulse, either it is logic 0 or logic 1. It is our wish to start. So we will start with the 0 first. So move AL comma 00H. So whatever the value which it is generated, we have to send for port A. So we will send this data to port A by using output A comma AL. So once this 0 is passed, we have to wait for some amount of delay. So we will call the subroutine delay by using call delay instruction. So after the required amount of time, then we want to generate the next pulse is logic. So for this purpose, we are going to write the AL with FF. Then we will send this one to port A. After sending FF, again we have to wait for some amount of time. So we will call the delay subroutine. Next, if you want a continuous pulses, so unconditionally we will go for jump to loop 1, where loop 1 again it will send 0, 0. So this is a generate a series of pulses. To end the program, we are going to generate the interrupt 21H and calling the function which is at 4CH into AH, then INT 21H. Then we will end the code segment by using code endes. To end the program, we will write the statement as end start. So this is the program for interfacing DAC for generation of square wave. If the delays of this logic 1 and logic 2, if you want a different delays, then you can have two different delay programs, call delay 1 and call delay 2. If D1 is equivalent to D2, it generates symmetric signal, so where we require only one subroutine. The next question is illustrate the pin diagram of 8255 programmable peripheral interface. So we know that 8255 is a programmable peripheral interface which is used to convert IO device to the microprocessor, where the 8255 is consist of 4 ports, that is port A, port B, port C. All these ports are 8-bit ports which we can group into two groups, that is group A and group B. Under group A we have the port C upper and port A, which will use the 12 bits size of IO pins, whereas group B, that is port C lower and port B, which will use the 12 pins of IO devices. So apart from that, we have the address lines A0, A1. This is mainly for differentiating either it is control word register or port A or port B or port C. Next, ground pin, which is for grounding the supply sources, and we have a VCC pin, which is need to provide the biasing voltage for the internal elements. Next, these are the port C pins, PC7 to PC0. Next, these are port B pins, 8 port B pins, port A 8 pins. Here it is a read signal and write signal. Whenever the processor wants to read the data from 8255, that signal will be indicated on RD bar. Whenever the processor wants to write the data, this signal will be connected to right pin of 8086 processor. So to enable the chips 8255, we are going to give the chip select as 0 because it is a active low signal. Next, the 8 pins of the data bus of 8086 processor is connected to a D0 to D7 pin of 8255. To bring the system to a known state, we have a reset. Next, describe the control word register of 8255 for IO mode and explain in detail. So we have two modes actually, BSR mode and IO mode. In the BSR mode, only port C bits we can go for set or reset mode. So in the BSR mode, the MSB bit is equivalent to 0 and the last bit it is used for either reset or set. Which pins we want to reset of the port C, that will be decided by D1, D2 and D3. If D3, D2, D1 are 0, 0, 0, bit 0 will be selected until 1, 1, 1, bit 7 is selected. So this is for only altering the port C pin. Either we can configure to set or reset. Whereas the second operation is IO mode, where in IO mode we can have 3 modes, mode 0, mode 1, mode 2. So the control word register for IO mode is MSB bit you will write as 1. The lower bit is a port C. So this port C lower we can configure either as input or output. If you write 1, it is going to configure in input. If you write 0, the port C lower will be configured as output. The next bit is corresponding to port B, similarly configuring either input or output. The next bit is a mode of selection for port group B, where we can have port B and port C lower. We can configure the group B in 2 modes, that is mode 0 and mode 1. The next bit is corresponding to port C upper. Here also the port C upper either you can configure in input or output. The next bit is corresponding to configuring the IO port, which is port A in the input mode or output mode. The next 2 bits are corresponding to the mode selection for group A, that is for port A and port C upper. 00 is for mode 0, 01 is for mode 1, 10 or 11 it will configure in mode 2. Illustrate mode 1 operation of programmable peripheral interface. So mode 1 means here we are going to have handshake signal or strobe IO. So in this mode, the port A and port B are used for data transfer, which will act as a IO ports, whereas port C is used having the control signal will called as handshake signal. In this mode, the inputs and outputs are latched. This output has interrupt handling capability and the signal control to match the speed of CPU and IO devices. So if you are using the mode 1 in input handshaking, so between the input devices and the 8086 processor, we have few handshake signals apart from the data transaction. So the various signals we are going to have here, it is IBF, which is input buffer full. Next we have the strobe signal, which is from the IO device to 8255. Next, once this strobe signal is generated, the interrupt is generated. Next, in the output mode, we are going to have the control signals are output buffer full, acknowledgement and interrupt. So whenever the processor wants to send the data to the IO device, first the data will be latched into the buffers, that is output buffer. So once the output buffer is full, then acknowledgement is given. Then this once acknowledgement is received, then interrupt will be generated to 8086 processor. Next, describe the 8255 programmable peripheral interface. So in 8255, we have group A port and group B ports, that is port A and port B, and these two are divided into two 4-bit ports, which is nothing but port C, and this is the internal bus, and this data bus buffer, which is used for interfacing the 8086 data bus with the internal data bus. And here we have a read-write control logic and group A control, some additional control signals we are going to have. Describe mode 0 operation of 8255 programmable peripheral interface. So mode 0, it is a simple or basic IO mode. So it is normal mode of data transfer. In this mode, all the 3 ports, port A, port B, port C, are used for data transfer. In this mode, all the ports can be used as input or output mode. The outputs are latched, but inputs are not latched. This mode, it has interrupt handling capability. It is less reliable because no handshake signals. Here, slow response devices cannot be interfaced easily. Next, we have classify modes of data communication. So in the various modes we are going to have is half duplex, simplex and full duplex. So in the simplex mode means where a device 1 will communicate with the device 2, but data transfer will be in only one direction. Either we can have from D1 to D2 or D2 to D1, only one direction. The next one is half duplex, where in the half duplex we have the two devices D1 and D2. These two devices can communicate it in both the directions. That means D1 can send the data to D2 as well as D2 can send the data to data. But here we have only one bus for data exchange. So as only one bus is existing, only the data can be transmitted either from D1 to D2 or D2 to D1 at a time. But both will not be takes place parallel. The third one is a full duplex, where in the full duplex, the data transaction between device 1 and device 2 will be takes place simultaneously, because a separate bus is there for D1 to D2 communication and a separate bus is there from D2 to D1. So in the full duplex, we can have the data exchange in both directions. Differentiate synchronous mode, asynchronous mode. Write the data formats in synchronous mode and asynchronous mode. So synchronous means the arrival of the data can be expected, whereas asynchronous mode means they are at a different frequency of operation. So arrival of or expecting of the data we can't explain. So in asynchronous communication, whenever we want to send the data, this data will not be sent directly. We are going to append few bits, the start bit, followed by data, then optional parity bit we can have. After parity bit, we are going to send the stop bits. This is the data format for asynchronous communication. Whereas for synchronous communication, so between two datas, let us consider I have a data packet 1, data packet 2. Here we are going to send some synchronous characters. Illustrate the significance of mode instruction control word of 8251. So we are going to see this mode instruction for both the synchronous mode as well as asynchronous mode. When we are configured for synchronous mode, the LSB bit, the next bit will be given as 00 for mode synchronous mode. The next two bits will give us what is the size of the data which we are going to be transferred. If you configure these two bits as 00, 5 bits transmission, 01, 6 bits, 10, 7 bits, 11, 8 bits. The next bit is either we want to enable the parity bit or not. So if you write this configured as 0, so the parity bit will be disabled. Only data will be sent, after that stop packets will be sent. Stop bits will be sent. If you enable, the parity bit will be enabled. And once you are enabled the parity bit, what kind of parity we can send? Either even parity or odd parity. So for that we can configure bit 5. The bit 6 and bit 7 is used to how many stop bits we want to send. Either 1 stop bit, 1.5 stop bits or 2 stop bits. So whenever you write 00, it is an invalid stop bit format. 01, 1 bit as a stop bit. 10, it is 1.5 bits, whereas 11, it is 2 bits. Here, 1 bit and 2 bits we are aware. What is 1.5 bit means? A stop bits pattern, how many clock pulses we want to send, we are going to send. 1 clock pulse, then it is 1 bit. 1.5 clock pulse, it is 1.5 bits. 2 clock pulses, it is 2 bits. Whereas for asynchronous communication, only the last 2 bits will be changes. 01, 1x time of the clock. 10, 16 times of the clock. 11, 64 difference will be there between the device and processor. And the remaining bits are same values. Next, illustrate the significance of command control word of 8251 UART. So 8251, the command control word is a 8-bit, where we are going to have the bit 0 as TXE, which is transmit enable. So whenever we want to transmit the data, first we want to enable the transmitter. So for that you will write the TXE bit is equivalent to 1. So this DTR, RTS, these two are corresponding to the modem operation. So data terminal ready, request to send. The next bit is to enable the receiver, we will configure RXC bit. So whenever the break characters we want to send, then we are going to configure send BRK as 1. Next, erase the flags. So whatever the data or whatever the data format which we are going to send, so if any errors are generated, to clear that we are going to configure this bit is equivalent to 1. Next, it is for internal reset. Next, hunt mode, external hunt. If you are looking for the synchronous characters, we will write EH bit is equivalent to 1. Explain the internal block diagram of 8251 UART. So the diagram shows, a figure shows the block diagram of 8251, which is USART, Universal Synchronous Asynchronous Receiver Transmitter. So the data whichever the processor wants to transmit, the data will be sent to the data bus. Then it will be stored in transmit buffer. Once the data is loaded into transmit buffer, it will send serially through TXT line. So at what rate the data has to be sent will be decided by transmit clock pulse. So once the data is transmitted and the buffer is empty, that will be indicated on TXE, which is transmitter empty. So the readiness of the transmitter will be indicated on TXRD. When the processor is receiving the data will be received serially. So what are the data which you are receiving, that will be buffered in a receive buffer. Once all the data is received, then this data will be sent to the processor through the data bus. This receiver will be controlled by the receiver control. The readiness of the receiver will be indicated on RXRDY. At what rate the receiver has to receive the data will be decided by RXC pin. So whenever we want to detect the synchronous character, how we want to define that, you can have the synchronous detector. Next, a read-write control logic, where we can reset the required clock pulses we can send on this line. Whether the processor is sending the control information or data transaction, that will be decided by C by D bar. If C by D bar is equivalent to 1, it is control information. If C by D bar is equivalent to 0, it indicates data transmission. Either the transmitted data we are getting from 8086 to 8251 or received data from 8251 to 8086 processor. Read write, the status of the processor, whether it is reading the data or writing the data, we can see on that one. Next, to enable 8251, we have chip select. Next, here we have a modem control. So through modem, if we are communicating, we have core signals, a DSR, a DTR, a CTS, and RTS. Data set ready, data terminal ready, clear to send, request ready to send, request to send. Next, a list of various errors occurs in serial communication using 8251 and elaborate each flag. So in 8251, we have various error flags like parity error, overrun error, and framing error. So parity error, at the time of transmission of data, even parity or odd parity bit is inserted in the data stream. However, at the receiving end, if the parity of the character does not match with the predefined parity, so then parity bit will be occurred. Next, overrun error. So in the receiver section, received characters are stored in the receiver buffer. So if CPU is failed in reading the characters loaded in the receiver buffer, the next received characters places the previous one and overrun error will occur. Framing error, if valid stop bits is not detected at the end of each character, then framing errors will be occurred. Next, model 2 8K cross 8 EPROMs and 2 8K cross 8 RAMs with 8086 processor. Here, they are given with 2 EPROMs and 2 RAM chips. We want to interface these memory blocks with 8086 processor. So first, for each RAM chip, as we are considering the RAM and ROM are of same size, so each memory chip is 8K size, where 8K we can write as 2 power 3 into 2 power 10, which will reduce to 2 power 13. So 13 address lines are required for accessing one memory chip. But here we have 2 memory chips. So as it is 2 memory chip, the total memory size is 8K plus 8K, which is equivalent to 16K. This 16K we can write as 2 to the power of 4 into 2 to the power of 10, which will give 2 to the power of 14. So 14 address lines are required. So out of 20 address lines of 8086, we require 14 address lines. So we are going to take the address lines from A0 to A13. And the remaining address lines, that is A14 to A20, that is A19, we go for decoding process. So when we are selecting from A0 to A13, we will write the bit pattern from 0000 to 1111 like this. The next bit corresponding to immediately to A13, that we will select, which is a A14, which will select for either it is a RAM block or a ROM block. So as we have two different kinds, only one bit is sufficient. So if A14 is equivalent to 0, so we will select the RAM block. If it is 1, that is A14 is 1, we will select RAM block. Remaining lines A15 to A19, we can give any pattern. So at reset, the CS and IP values will be generated. The address is FFFF0H. So if you observe, the higher bits are indicates F, means all the bits are equivalent to 1. So whenever we are designing the interface to meet this requirement, we will write the higher bits as 1. So for interfacing, the first one is, first we have to generate the address mapping. Once the address mapping is generated, then the decoding circuit. So the decoding circuit will be consist of BHE bar A0, which is going to decide how much amount of data transaction, either it is 16-bit or upper 8 bits or lower 8 bits. So as the data transaction is with respect to ROM or RAM, so one more control signal will be used. In this example, A14 will be used. So once the decoding circuit is done, then we have to find the logic for chip select. So these are the various steps which we are having to model the memory interfacing with 8086 processor. So in this session, we have discussed a question as related we can expect from the unit 2. which is interfacing devices. So where we have discussed a few questions to 8255 IO interfacing like ADC and DAC and stepper motor. Then we have discussed USART, where we can have the serial to parallel or parallel to serial. We can have conversion through 8251, which is USART, Universal Synchronous Asynchronous Receiver Transmitter. At the end, we have discussed just briefly about the memory interfacing with 8086 processor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.